Magnetic levitation, or Maglev trains, represent a cutting-edge advancement in transportation technology, utilizing magnetic forces to achieve frictionless travel. Unlike conventional trains which rely on wheels and tracks, Maglev trains float above the guideway, propelled and levitated by magnetic fields. This innovative technology is not only transformative in terms of speed and efficiency, but also offers a quieter and smoother ride. Understanding how Maglev trains work involves delving into the principles of electromagnetism and the specific technologies used to achieve levitation and propulsion. Principles of magnetic levitation. Magnetic levitation trains operate based on fundamental principles of electromagnetism, primarily the interactions of magnetic fields. These principles include 1. Electromagnetic force. When electric current flows through a conductor, it generates a magnetic field. Conversely, a changing magnetic field can induce an electric current in a conductor. Maglev trains exploit these interactions to create forces that can levitate and propel the train. 2. Magnetic repulsion and attraction. 2. Like magnetic poles repel each other, while opposite poles attract. Maglev systems use these fundamental interactions to create lift and propulsion without physical contact between the train and the track. Types of Maglev systems. There are primarily two types of Maglev systems: electromagnetic suspension, or EMS, and electrodynamic suspension, or EDS. Each uses different methods to achieve levitation and propulsion. Electromagnetic suspension, or EMS. 1. Components. In an EMS system, the train is equipped with electromagnets on its undercarriage, while the guideway or track has permanent magnets or electromagnets. The core idea is to use the attractive and repulsive forces between these magnets to control the train's position. 2. Levitation. The train's electromagnets generate a magnetic field that interacts with the guideway's magnets. By adjusting the current in the electromagnets, the system creates a repulsive force that lifts the train off the track. To maintain levitation, the system continuously adjusts the magnetic forces to keep the train at a stable height. This is achieved through sophisticated feedback loops and control systems that monitor the train's position and adjust the magnetic fields accordingly. 3. Propulsion EMS systems use linear motors for propulsion. A linear motor generates a moving magnetic field along the guideway. This moving field interacts with the train's electromagnets to create a thrust force that propels the train forward. By varying the frequency and strength of the current in the guideway's electromagnets, the system can control the speed and acceleration of the train. 4. Advantages and challenges. EMS systems provide precise control of the train's position and can achieve high speeds with minimal friction. However, they require complex control systems and can be sensitive to changes in the magnetic field, which may affect stability and ride quality. Electrodynamic suspension, or EDS, systems use superconducting magnets, which are magnets made from materials that exhibit zero electrical resistance at very low temperatures. These superconducting magnets are cooled using liquid helium to maintain their superconducting state. The guideway typically contains either permanent magnets or electromagnets. EDS systems leverage the Meissner effect, a property of superconductors that causes them to expel magnetic fields from their interior. When superconducting magnets on the train interact with the guideway's magnetic field, they experience a repulsive force that lifts the train. This repulsion is inherently stable, making EDS systems less reliant on complex feedback control systems compared to EMS. Similar to EMS systems, EDS systems use linear motors for propulsion. The moving magnetic field along the guideway induces a force on the superconducting magnets of the train, pushing it forward. The frequency and strength of the magnetic fields in the guideway can be adjusted to control the train's speed. EDS systems offer greater stability due to the repulsive forces between superconducting magnets. However, they are energy-intensive because of the need for cooling superconductors with liquid helium. Additionally, the high cost of superconducting materials and cooling systems presents a challenge. Maglev trains offer several significant advantages over traditional rail systems. The primary benefit of Maglev technology is the reduction of friction. Since the train levitates above the track, there is no physical contact between the train and the guideway. This lack of contact eliminates rolling friction, which is a major source of resistance in conventional trains. The reduced friction allows maglev trains to achieve very high speeds. For example, the Shanghai Maglev, which uses EDS technology, can reach speeds of over 430 km per hour or 267 miles per hour. This speed is significantly higher than that of conventional trains. The absence of physical contact with the track results in a smoother ride with minimal vibrations. Additionally, there is no wheel noise, making the train operation quieter compared to traditional rail systems. Without physical contact between the train and the track, there is less wear and tear on both components. This results in lower maintenance costs and a longer lifespan for both the guideway and the train. Despite their advantages, maglev trains face several challenges. The development and construction of maglev infrastructure involve high costs. Building new maglev tracks and stations requires significant investment, making it more expensive compared to upgrading existing rail systems. EDS systems in particular are energy-intensive due to the need for cooling superconductors. The energy required for maintaining the superconducting state can impact the overall energy efficiency of the system. Integrating maglev systems into existing transportation networks can be complex. The construction of dedicated maglev tracks and stations requires careful planning and significant investment. Ongoing advancements in materials and technology are needed to make maglev trains more cost-effective and efficient. Research into new superconducting materials and alternative cooling methods is essential to address some of these challenges. Magnetic levitation trains represent a revolutionary approach to rail transportation, leveraging electromagnetic principles to achieve high-speed, frictionless travel. By using either electromagnetic suspension, or EMS, or electrodynamic suspension, or EDS technologies, maglev trains eliminate the need for traditional wheels and tracks, resulting in a smoother, quieter, and more efficient mode of transport. While challenges such as high initial costs and energy consumption remain, ongoing advancements in technology and materials hold promise for making maglev trains a more viable and widespread solution in the future of transportation.